In the last lecture, we were discussing about finding the ground state, finding the minimum for the potential and how to expand around that. So let's start from a few examples. Let's start from a simple example where the potential has the following form. Let's say the potential is simply m square phi square minus c. Okay. So in this case you can just write it as m square minus phi square minus m square c. Let's call it a m square a. So that then the minima is clearly phi is equal to 0. Right? How do we do that? The way we do that, we evaluate v prime of phi, which is simply m square phi, and then it is only 0 when phi is equal to 0, and then we also compute v double prime of phi, which is m square, which is clearly greater than 0. So this is a minima of the potential. So this minima of the potential we denote as phi c. Okay, phi c. So the way we write the quantum field in this case is phi c plus phi hat. Okay, so in this case this is 0. Sorry, this is fluctuation. In this case this is 0, so there is no distinction between phi and phi c. So let's consider another example. Let's say the v of phi. We will increase the complexity one by one. So let's say v of c is m squared times phi minus a whole square. Okay. So in this case v prime phi is m square phi minus a, implies that the classical ground state phi c is simply a. Okay. So then if we write down the quantum, sorry, this was wrong. If we write down the quantum field as the thing plus small fluctuation, then this is just a plus phi c. Okay. Then the potential for the fluctuation is simply half m square phi hat square. Okay. So in general, that means in general, if I have a potential phi, v of phi, and let's say that phi c is a global minima. Phi c is a global minima. Then we can write down the potential always. Okay, phi c is a global minima. So we write phi is equal to phi c plus phi hat. So minima, actually, okay, this is fluctuation. Actually, we must write it in a bit elaborate way. So this depends on space time, the field, and the fluctuation also depends on space time. But the ground state solution, the classical vacuum solution, that solution is space time independent. Okay, because we solve time independent, space time independent. This implies that the kinetic term, the del mu phi term, simply goes to the fluctuation kinetic term. Okay. And the potential term v of phi is some v of phi c plus phi fluctuation, not this fluctuation. This can be written as the functional value of the potential at that point plus, I am just Taylor expanding, Vc of phi hat, but this is 0 because it's a minima. Then V double prime phi c half phi hat square plus dot dot dot. Okay, so this we have to do. So we have to, let me repeat again. Find the global minimum, expand the field in small fluctuations, around the minimum, and then write down the action for the fluctuation. Okay, this is important step to set stage for quantization. Because you remember that when we quantize fields in the method we are following here is in canonical quantization. So in canonical quantization, we quantize fluctuations, not the field itself. We quantize fluctuations, not the full field. Okay, this is, you should remember that in canonical fluctuation, this is what we do. When you go to path integral formalism, this statement will change a bit, but in canonical quantization, that's we do. So we saw that here the kinetic term, the potential term usually have quadratic piece and then cubic piece and then quartic piece. But again, for simplicity, let's make another simplifying assumption. We will relax it, and we will relax it in the course very soon, and the most course is about how to relax that condition. But for the moment, make the simplifying assumption that restrict the action for small fluctuations up to quadratic order. Okay. So the thing that then we want to actually discuss is the following thing. After this simplifying assumption, our action is simply d4x del mu phi hat del mu phi hat minus let's say, okay, so you put a half here, half m square phi hat square, okay, where phi hat is a function of space time. Great. So we have set the stage for our starting point to understand the system. But again, rather than understanding this fourth dimensional thing, from 3 plus 1 Minkowski. Let's go to 0 plus 1 Minkowski. Again, it's a simplifying assumption, and we will relax it again by the end of the next lecture. So then we are really in a case, we are studying a system where okay, so we completely forgot the space part. We forgot the spatial directions. There is no rational, there is no physical reason for this. At this point, the justification is really that we want to simplify the system the most, so that we can study it and then we will later come back to this. Good. So this is our system. And in this case, the time t takes value from minus infinity to plus infinity. And the fluctuation also takes value from minus infinity to plus infinity. Okay. Now, another thing, so before we move on to the discussion, we assume that m is not equal to 0. Okay. M equal to 0, is a subtle case. We have to discuss it separately. Great. So now, whenever somebody gives you a Lagrangian, what's the first thing you should do? The first thing you should try to see is that what are the symmetries of your theory. And here we have a lot of symmetry. So first symmetry is that time reversal symmetry. So what happens is that this is a space-time symmetry. So under that t goes to minus t, and phi of t goes to minus, not minus, phi of minus t. So this is space-time symmetry. Okay. Since this is a discrete symmetry, there is no conserved charge. Okay. So next symmetry is time translation symmetry. Time translation symmetry. So under time translation symmetry, so this is a continuous space-time symmetry. So under time translation, you can so t goes to t plus c, phi goes to phi of t plus c. C is a real number. Okay, and since this is a conserved quantity, since this is a continuous symmetry, comes with a conserved quantity. So in this case, the corresponding conserved quantity is simply, you can compute it. In this case, the corresponding conserved quantity is this, and this is nothing but the Hamiltonian. Okay. Also, there is another very important symmetry here. There is another symmetry here. Which is a field space Z2 symmetry. So this is a field space symmetry. It has nothing to do with space time. Okay, and the field space under field space S2 symmetry, what happens is that the field just goes to minus of itself. Okay, so these are the three symmetries that our system has. So when we'll go to quantum system also, we have to understand that how these symmetries actually act on the Hilbert space and all these things. Now we will study quantization. Oh, great. So in order to study quantization, as I said earlier, that the way we quantize is that we promote Poisson brackets to commutator brackets. So in order to compute Poisson bracket, first we have to compute the canonical momentum. And in this case, the canonical momentum is simply phi dot. Okay. So in this case, the canonical momentum is simply phi dot, which means that the quantization rule is the field and its canonical momenta. The bracket is IH bar. The field commutes with itself, and of course the momentum also commutes with itself. Okay. So it's worth stressing it again that when we quantized here, we use the action for the small fluctuations. We are not quantizing the full field. We are just expanded this in the field in small fluctuations, and then we constructed the action of the small fluctuations, and then we found the canonical momenta for the small fluctuations, and then we are quantizing it. Okay. So now, in order to proceed, it's useful. It is useful to write phi and pi in terms of two operators, phi and pi. And the way we write it is that phi is simply h bar by 2m, a plus a dagger, and pi is minus I m h bar by 2 a minus a dagger. You can verify that phi dagger is phi and pi dagger is pi. Okay, the way we wrote it, we made sure this thing. Then from the canonical commutation, from the canonical commutations, it follows that the commutator of A and A dagger is 1. E commutes with itself, and also A dagger commutes with itself. Okay. Good? All good? Great. Next step is that we write the Hamiltonian. In terms of A and A dagger. Okay, so our Hamiltonian is actually half pi square plus half m square phi square. Okay, this is just the way you derive it is just you just Legendre transformation from the Hamiltonian. So this is just nothing but, so Hamiltonian is just pi phi dot minus the Lagrangian, and then you get this. This is the Hamiltonian. Okay, you just substitute the expression and you will get these things. Now if you substitute the expressions for phi and pi from here, it's just a simple algebra to show that. So substitute these expressions. And substitute these expressions. The Hamiltonian you will arrive at is simply h bar m A dagger A plus half. Okay, so this is just, what did you do? Substitute phi and pi in terms of A and A dagger. Okay, good, very good. Okay, now let's try to derive some useful formula. So let's try to compute the commutator of A dagger A with A. The commutator of A dagger with A is A dagger A plus A dagger A commutator A, which is same as minus A, because this thing is minus 1 and this is 0. Okay, so the same way we can compute, in the same way we can compute A dagger A commutator A dagger, and you will find that this is simply A dagger. These two relations imply that the Hamiltonian commutator A is minus h bar m A, and the Hamiltonian commutator A dagger is plus h bar A dagger. Okay, this implies that, let's say that we have found a state E, which is the eigenstate of the Hamiltonian with energy E. Then from the above commutation relation follows that A acting on E has energy E minus h bar m. How do we do that? The way we do that is simply, let's act H on this. This is simply a H commutator A acting on E plus AH acting on E. And then we get this is minus H bar M A E plus A E E. So E minus in the same way you can also show that if I construct A acting on E, then this has energy E plus H bar M. Okay, that's why A is called annihilation operator, as if it annihilates energy. And A dagger is called creation operator. Okay, you probably studied in your quantum mechanics course. This implies that the lowest energy state, must be annihilated by A. So this is the lowest. If this is the lowest energy state, then lowest energy state must be annihilated by B. Because if it is not annihilated, then you can create another state which has lower energy than this. Okay, that's the simple logic. Very good. If that's the case, then this is annihilated by E, which means that the Hamiltonian acting on this is H bar M A dagger A plus half acting on that is half H bar M. And this is called 0 point energy. This thing is called 0 point energy. Okay, this is extremely important because you see that what the 0 point energy does, it says that even if the classical lowest energy state has zero energy, the quantum lowest energy state actually has non-zero energy. So the classical lowest energy state is no longer a quantum mechanically allowed state. The quantum mechanical state should have some more energy. Okay. Now, which means that if this this thing is the lowest energy state, we can create higher energy state by action of A dagger. Okay, so what do we mean by that? Let's say A dagger acts on this, then this must have energy, this has energy 3 by 2 H bar M. Okay, so in the same way you can show that if you construct A dagger M then this has energy N plus half H bar M. Okay, check it. So since in harmonic oscillator the states are in integer spaced, okay, it is useful to denote the state. So firstly note that there exists an operator, N which is A dagger A such that each commutator N is 0, which means that N is a conserved quantity. Okay, So under the time evolution, the n quantum number won't change. And this allows us to denote the basis elements of the eigenvectors by n quantum number. So this means the vacuum or the ground state quantum ground state, or this is also called vacuum. We will denote it as 0 because we found from here that n acting on the ground state is 0, and then any higher nth occupation state n is simply a dagger n acting on the vacuum. Okay, there will be a normalization here. We'll come back to the normalization, and these are the states in the Hilbert space. Okay, these are the states. Now the normalization is easy to fix, that you want n equal to 1, which implies that you want 0 a power n, a dagger power n, 0, n square is equal to 1. And if you do that, you can show that n square must be 1 over n factorial, which means that n is simply 1 over square root n factorial. Okay, so this is the way, which means that the normalized states, the eigenstates of the Hamiltonian is simply n, where n is a dagger acting n times on vacuum divided by 1 over n factorial, and n is a positive integer. Okay, so today we just found the Hilbert space. Next time we'll start from the Hilbert space, and we will study dynamics, and we will also study that how various symmetries act on this Hilbert space. Okay, so we stop here.